I'm Rachel McDowell, and me and Olivia are going to give the presentation for the basics of soil science and renewable energy.
Before you start, would you
Yeah,
please show your faces and
yeah,
your organization
Thank
and
you for
what
reminding me.
you do?
yeah, sure. Hold on, yeah, there you go. You can see our faces now. We're good? Okay.
All right. Well, thank you all for joining us and taking the time with us this afternoon to go over some soil science stuff. And as Havita mentioned earlier, if you didn't hear though, we really welcome any questions y'all have at the end of our presentation, whether it be you just speak up over camera or if you want to put a question in the chat. So yeah, my name's Olivia Peters. I am a soil health specialist out of the Fresno area office for the USDA Natural Resources Conservation Service. So I cover from Tulare County up to Nevada County. And I'm also the California LGBTQI plus special emphasis program manager for California NRCS. And I've been with the agency for about 2 years. Rachel?
Okay. So my name is Rachel McDowell, and I'm the soil health specialist for Area 1. So it's the same position as Olivia. It's just in a different area. And so I cover Northern California. So my office is located in Oroville, kind of close to the foothills area. There's a little picture of me at Table Mountain the other weekend. The waterfalls were going. And so my area goes from the border with Oregon up to that area, all the way down to like Woodland, California. And I've worked for the NRCS for some going on 4 years. This will be my fourth year. So, all right, so we're good. I'm gonna get into it. Me. Okay. Okay, so these are some pictures that I took of different land uses in the area where I am. So there's a variety of different land uses. There's crop. So I have an almond orchard. There's cropping systems, orchards, there's a range. And so I have a picture of rangeland where range and forestry, sometimes they sort of blend together a little bit. You get a lot of forested areas mixing with like rangeland. And then there's like pasture systems where you have paddocks, and you can see the little paddocks where they rotate the livestock out. And there's also urban kind of residential areas. I took this picture of someone who wanted conservation technical assistance, and she was just trying to improve some portion of her residential lawn area. So urban is more of like those smaller scale suburban projects that involve more like hands-on kind of work. So gives you an idea what different land uses look like. And so now that you're more familiar with different land uses, we can get into ecological site descriptions. So ecological site descriptions, if you have an ecological site is referring to a distinctive kind of land that has very specific soil and physical characteristics. And so these characteristics differ from other kinds of land. due to their ability to produce very specific kinds and amounts of vegetation and its ability to respond similarly to different management actions and natural disturbances. And so for an ecological site, you'll look at use of different climate, soil, geomorphology, hydrology, vegetative information to describe ecological potential for the land area. And an ecological site can feature several plant communities that occur over time and in response to different management actions. And so I included this image from the UC A&R manual from 2022. And I just think it's a really good picture because it shows the intersection of all these different ecological sites. So it shows shrubland, grassland at the foothills of the Tehachapi Mountains in Tejon Ranch, California. I think it's somewhere close to like Bakersfield. And so this just shows you how the different ecological sites intersect and how they vary. And the authors of this publication found that the soil carbon varied significantly between different ecological sites, vegetative states. That really changes things. And so when you kind of have an idea of what ecological site is, you can write an ecological site description. So ecological site description is a report that describes biophysical properties of an ecological site, vegetation, and surface soil properties are like you have a reference condition. And so your reference condition usually represents the pre-European vegetation before America started getting all these immigrants coming in and, you know, taking things out and putting things in that weren't native to the area. And the historical range of variation or proper functioning condition, the potential for the natural vegetation. And so we got to have those reference conditions. And then ecological site description will have a state transition model with graphics and text. And so ecological sites they can go forward and backward, and they can transition and they can transition and reverse and kind of go into different states and transitions. They're not static things. And they change over time. And so the state transition model has to account for that. And so then you would look at also a description of the ecosystem services and all of that. If you're writing an ecological site description, all of that goes into a report. And so in the US, ecological site descriptions are connected to a spatial data via soil map units of the National Cooperative Soil Database. And so these soil map units can be visualized through Web Soil Survey, which is a product of the USDA NRCS, or within a personal GIS file via Sergo. And ecological site descriptions can be used to stratify the landscape for monitoring, assessment, interpreting resource hazards, opportunities, prioritizing where management actions need to take place. And so the state transition model synthesizes literature and formal knowledge, and it's designed to a specific ecological site to determine how changes in vegetation and soils can easily are reversible versus changes that are subject to a threshold, which is beyond reversible, because it'd be costly or impossible. So certain things, qualities in soil, you can easily reverse, and other Other qualities, it's much harder to reverse. And it's important to remember that when you have a soil map unit, it could contain multiple different ecological sites. And an ecological site could contain multiple soil map units. And there is no one-to-one correlation between an ecological site and a soil map unit. It's just more intermingled than that. And you can have soil map units that have components, like different soil components that intermingle and form complexes. And so it's not always one-to-one. It's not always just everything can be separated out neatly. And so this shows how an ecological site can be broken down based on the example that I showed earlier at Tejon Ranch. And so they had two different vegetative states. They had shrubland and grassland, and they divided it up based on the elevation. So you can see how the vegetation is changing as the elevation is increasing and going up. Those are kind of different communities within that. And so in the lower elevation, you have sediment from adjacent mountains and hills. And at the really high elevation, you just have sandstone and conglomerate. And so, yeah, so it just shows how they were all sampling these different plots, and the shrubland plots had 3 microhabitats and the base of the shrub, the edge of the shrub canopy, and the soil and the grass plant plots was collected randomly. But you can see just like the different, how it's all kind of mapped out differently to get an idea. And then, so the concept of soil health is based on the idea that chemical, physical, and biological properties, they all like overlap with each other. You can have soil biochemistry, you can have biophysics, you can have, geochemistry. It's all kind of like, it all kind of overlaps together. And so when you combine all of those different characteristics, that's how some people describe soil health. So soil health is the capacity of the soil to sustain plant and animal productivity, maintain or enhance water and air quality, and support human health and habitation over a human timescale. So it's really how the soil is able to retain all those ecosystem services. And the NRCS has principles of soil health that we try to educate people about: minimizing disturbance, so reducing the amount that you till, that's important; reducing passes, heavy machinery; maximizing biodiversity, integrating livestock, and rotating your crops, doing things like that; maximizing soil cover, so getting more mulch, getting more residue, getting it so the soil's not bare and exposed to erosion; maximizing living roots, so having something growing on the soil year round, not having just bare soil with nothing growing on it. And so the principles of soil health is about keeping things going and not having that bare, low productivity. And so this is a illustration of the carbon cycle, and it's important to understand the carbon cycle when thinking about renewable energy and soil. So some carbon will remain in the atmosphere and it won't go into the cycle. But if you look at the diagram, you can see all the different ways that carbon gets emitted into the atmosphere. So there's volcanoes, there's transportation, there's fire, agriculture, fossil fuel emissions, animals, and little bit from the oceans. And then you can see the different ways that carbon is sequestered. So it's sequestered through plants, through wetlands, and it can be sequestered in the oceans as well. And then so the things that sequester carbon, they help carbon decompose. And then ideally, some of the carbon would remain in the ground, and the soil is a really huge way to sequester carbon. And so this diagram shows how carbon dioxide emissions have changed over time. So beginning in the mid 1700s, the world really started to change a lot. People became much more dependent on machinery to complete day-to-day activities. And that's really where carbon emissions started to increase, because people were using these non-renewable fossil fuel sources to power these newly invented machines. And so these machines were a product of the Industrial Revolution. And so they included like automobiles, factories, all kinds of things like that. And so the more and more and more our society became dependent on those for day-to-day functioning, you can see it just keeps going up. So the more carbon that is emitted through machinery, the more it's going into the atmosphere. And so I guess this is why there's been such a big push for renewable energy, because a lot of the machinery and vehicles and things that we use are not very sustainable in terms of the amount of carbon that they're putting in the atmosphere. And so for soil organic carbon, there are 3 different types of soil organic carbon. There's the living, which is plant roots, bacteria, fungi, nematodes, numerous other types of organisms. These all decompose organic matter, they cycle nutrients, they suppress pathogens through various physical chemical responses. And then there's the dead, which is like recently dead soil organisms and plant residue that will provide energy and nutrients. It's also called active or particulate organic matter. And then there's like the very dead, which are not biologically active fraction, well decomposed organic materials, humus. It supports chemical activities. They contain high amounts of negative charges. They hold nutrients and cations in the soil. And then they also have a very high water holding capacity. But it's just, that's the part that's kind of calcitrant, that's not very active. So I like to think of it that way: the living, the dead, the very dead. It's like the good, the bad, and the ugly. It's like that kind of thing. And then, so there's carbon sequestration. So you have geological, there's 2 different types of carbon sequestration. You can have geological, which is the process of storing carbon dioxide in underground geologic formations. And then the CO2 can become pressurized, it becomes a liquid, it's injected into like porous rock formations, into geological basins. So that's geological carbon sequestration. But the kind that most people think of when you say carbon sequestration is biological, but they usually don't put the biological in front of it. But that's usually what people think of. It's storing atmospheric carbon in vegetation, soils, woody products, and aquatic environments. And so this diagram shows the concept of geological carbon sequestration. So you have the contribution to this CO2 by human activity from land use changes, electricity generation, energy demand, transportation, petrochemical, manufacturing. And then you have carbon capture technology, which supposedly would be able to take the carbon emissions and kind of put them back into through residual trapping, it'd be able to put them back in somehow. And then biological carbon sequestration, so taking advantage of the natural ability of life from ecosystems to store carbon. So big things that store carbon are like forests, peat mosses, coastal wetlands, and those are pretty good. And then microorganisms break down plants and animals through decomposition. And then plants store carbon in their tissue, their bark, their root systems. And there is also carbon storage from oceans and coastal wetland ecosystems. And this is thought of as blue carbon. And then this is another diagram which illustrates soil, land, and climate change. And so the soil contains large amounts of carbon and nitrogen. And you can see how climate change, it just illustrates how we have greenhouse gas emissions, desertification, melting of permafrost glaciers, deforestation. And like those are kind of the things that are leading to climate change. And then you have, with the changes from climate change, you're going to have more flooding. You're going to have loss of organic carbon. You're going to have like soil erosion. You might have changes in the yields of crops. We might have to become more dependent on biofuel crops. And so land use affects the atmospheric composition of carbon. And that's a big influencing factor with how much carbon is going into the soil. Clearing or planting forests, melting the permafrost, all of those things can shift the greenhouse gas emissions for better or worse. And so climate change will ultimately affect the location and the kinds of crops that are going to be produced. And then I was just going to finish with a quote that I found, and it is by a global yogi. His name is I think it's Sadhguru, and he has done a global campaign for the advancing of soil health for about 3 decades. And he believes that soil health is our life, our very body. And if we forsake the soil, in many ways, we forsake the planet. So his campaign has really stressed the importance of soil health, maintaining organic carbon, increasing biodiversity, providing habitat for animals through the soil, and that the soil is just the way of keeping carbon out of the atmosphere. And he's done a lot to kind of push for some change within that and advance those causes. So I thought I'd finish with that. And now Olivia can move over to her section.
Yeah, thanks. So now that y'all have kind of an overview of soil and renewable energy and climate change, I'm going to go over some soil science basics and just kind of get into the nitty gritty. I'll try not to go too in depth, but try not to rush, and we should have time for questions at the end. So looking at soil composition, aside from water and air, there are 2 main components in soil. I have a diagram of the ideal soil, which would have a decent organic fraction and then but still majority mineral. So the 2 components in soil are the organic matter and the mineral components. So organic matter can include anything from plant residue to humus and organisms, while the mineral component contains primary macronutrients, secondary macronutrients, and micronutrients. So the primary macronutrients, I'm sure you're all familiar with, nitrogen, phosphorus, and potassium. They're the most important for plant growth and needed in the largest quantities, while your secondary macronutrients are not quite as important, and most of them are readily available, such as calcium, magnesium, and sulfur. Micronutrients are like they sound, they're just needed in much smaller quantities. And I'd like to take a minute just to distinguish between essential versus beneficial nutrients. So essential nutrients are those nutrients that are required for plant growth and sustain life. So if a plant does not have access to essential nutrients, it could be stunted or die. Whereas beneficial nutrients, they still benefit the plant in some way and benefit plant growth, but they're not essential for that plant to thrive and to live. Next slide, please. All right, and soil moisture regimes. So there are 5 soil moisture regimes. So the first one I want to talk about is the aqueic soil moisture regime. So this one would be kind of described as if you think of like Florida, the Everglades really, then they're saturated. Basically, the soil is saturated and free of gaseous oxygen for long periods of time, which results in glaying and mottling due to those anaerobic conditions. Eutic soil moisture regime has sufficiently high water content most years to meet plant needs, whereas aeritic is dry for at least half of the growing season, and the soil will not be moist for more than 90 days consecutively. Eustic is kind of intermediate between eutic and aeritic, so there's some plant available water during the growing season, but some droughts can occur still. And then xeric is much what we experience here in in lots of the Central Valley. So that kind of Mediterranean type climate, where you have cool, moist winters and warm, dry summers. Next. Soil temperature regimes. So as you can see, I kind of just made a table to lay it out as concisely and clearly as I could. So it's all based off of the seasonal fluctuation in soil temperature and also the mean annual soil temperature. So with a mast of 0 to 8, it could be, and a seasonal fluctuation greater than 6 degrees Celsius, you can have a cryotic or a frigid soil temperature regime. The only difference there is that frigid is going to have slightly warmer summers than cryotic. Cryotic is the coldest of the cold, but they're still going to fall within that 0 to 8 degrees Celsius range. 8 to 15 degrees Celsius would be mesic. A mast of 15 to 22 degrees Celsius is thermic, and anything over 22 degrees Celsius is hyperthermic. Now, if the seasonal fluctuation is less than 6 degrees Celsius, that we're basically just going to attach that prefix ISO onto the temperature regime from before. So mast of 0 to 8 that has a seasonal fluctuation less than 6 degrees Celsius would be isofrigid. Next would be isomesic, isothermic, and isohyperthermic. Next. So looking at soil formation, we have 5 main soil forming factors, being parent material, biological activity, climate, topography, and time. So parent material is really looking at the lithosequence, but the rate of soil formation is more dependent on texture, mineralogy, and coarse fragments derived from those parent materials. Biological activity is determined by the parent material, climate, relief, and organisms, and it can change over time. Climate, we're really mainly looking at temperature and precipitation. And with topography, we're going to look at those aspects of elevation, slope aspect, and slope gradient. And there are additionally 4 soil forming processes that we're going to look at. So those are additions, which are any inputs of materials from an outside source. Losses, any loss of material from the soil profile. Transformations, which are chemical or physical modifications or destruction of soil constituents through synthesis from the precursor materials. And translocations, movement of inorganic and organic materials laterally or vertically through the profile. Next, please. So to dive in a little bit more, I've listed some types of biogeochemical weathering. As Rachel mentioned, there's a lot of overlap in soil disciplines. So here you can see that clearly, biogeochemical weathering. An example being hydration, where water binds to a mineral. Hydrolysis occurs when the water molecule splits into a hydrogen ion in a hydroxyl group. And the hydrogen will replace a cation from the mineral structure itself. Dissolution occurs when water dissolves a mineral by dissociating the cations and the anions. And acid reactions accelerate weathering very quickly. Oxidation and reduction occurs when there's a swapping of electrons between two elements, one being oxidized, one being reduced. The one being reduced being the one that accepts the electron. Next, please. So now diving into some soil physical properties. There are quite a few, but I tried to hit the main ones on this slide. So color is really big, looking at organic matter content, iron oxides, anything like that. And it's defined by hue, value, and chroma. Texture is defined as the proportion of sand, silt, and clay, and structure being the arrangement of sand, silt, and clay, characterized by grade, shape, and size. Available water holding capacity is also a very important physical property. Bulk density, being a great indicator of compaction, can be calculated by dividing the oven dry mass of the soil divided by the total volume of the soil. And porosity can be defined and calculated doing the volume of the fluids over the volume of the total volume of the soil. And fine texture typically results in more small pores, micropores, resulting in a higher porosity, whereas a coarser soil will have larger pores, those being macro or mesopores, and they tend to have a lower porosity. Aggregate stability is also very important in soil health and a great indicator of good soil structure. And saturated hydraulic conductivity, which really just describes the movement of water through soil when it's already saturated. Next, please. So looking a little closer at soil texture, there are 12 textural classes total. I tried to give a good little definition of them off to the left, but honestly, I'm more of a visual person. So I really like to look at the soil textural triangle. But basically sand particles are going to be between 0.5 or 0.05 and 2 millimeters. Clay particles will be less than 0.002 millimeters, and then silt is in between there. So anything also anything greater than 2 millimeters is not going to be considered a soil particle. That's going to be some type of rock fragment, gravel, etc. So, next, please. Looking at soil chemical properties, pH is definitely a very important property because it determines the solubility of minerals and nutrients. So the nutrients and minerals can't be taken up by the plant if they're not in the soil solution. They're not going to be in the soil solution if they're not soluble. So having a good soil pH is really important for nutrient uptake and availability. Additionally, cation exchange capacity is very important. It describes the maximum adsorption of cations to the soil colloid. The more surface area you have, the higher your CEC is going to be because there's more sites on the colloidal surface to absorb those nutrients and minerals. The CEC is really it's really made up of the clay and the organic matter content. They have the negative exchange sites where they can absorb onto those cations. And also importantly, as soil pH increases, the CEC is going to increase because you have more exchange sites, a more negative soil surface. So there's going to be more capacity to attract and hold on to those positive charges. Electrical conductivity or salinity is also very important, especially here in the Valley, and all over the state of California, actually, in a few locations. And then the sodium adsorption ratio is also important if you're trying to determine acidic soil. Um, so basically, the idea behind this is that monovalent cations cause dispersion in the soil. So, and sodium being a monovalent cation, it causes dispersion in the soil. So, if you have a really high sodium adsorption ratio, you could have acidic soil, which is not good for soil structure and aggregation and all those things. Base saturation is the percentage of the cation exchange capacity occupied by those base cations. So the main ones that we look at in soil for the most part are calcium, magnesium, and potassium. And ideally, you'd like a ratio of 20 to 4 to 1 with those ions. Soil organic carbon is also very important when measuring soil health, and enzyme activity. Enzyme activity is a great indicator of microbial activity and decomposition. Yeah, next. So looking at soil nutrient absorption specifically, the cation exchange capacity is very important, but first I'd like to distinguish between absorption and adsorption. So absorption is like, you put lotion on your legs or something. It's absorbing into your skin. However, adsorption is like you get a permanent marker and mark on your hand. That's not absorbing into your skin necessarily for the most part. It's adsorbing. It's just clinging to the surface. So when we're looking at how nutrients are absorbed, like I said before, they first must be in the soil solution. Luckily, most of our essential and beneficial nutrients are cations, and so they're held well to that soil surface. But a cation exchange reaction has to occur for soil nutrient absorption to occur. So, namely, the root hairs will exude a hydrogen ion, and that hydrogen ion will knock off a cation into the soil solution that can then be absorbed by the plant roots. But overall, with cultivation and plants in general, you will see the hydrogen concentration increase over time because the root hairs have to exude hydrogen to knock off those minerals and nutrients for uptake, and also because of respiration in the root cells. So I'll just do a quick little knowledge check. Anyone can feel free to shout out the answer if you want, or I'll give it 5 seconds, and if no one has anything to say, I'll just briefly go through it. So to release 1 calcium cation into the soil solution, how many hydrogen ions must be exuded from root hairs? Okay, I'm going to go through it. So calcium ions, they have a +2 charge. So to knock off 1 calcium ion, you're going to need to exude 2 hydrogen ions, since they only have the 1 proton there. But also just looking at cation exchange capacity in different clay types and soil textures, there's a great table here on this PowerPoint to look at the different types of clay and how their capacity for absorbing cations to the surface. So as you can see, sand has a very low cation exchange capacity. It's a very coarse particle. It doesn't have a lot of surface area compared to clay, which has a higher cation exchange capacity in general. So yeah, next. Looking at nutrients from soil to plant. So nutrients can be absorbed in 3 different ways. So first, there's root interception. So if the root is already in contact or in close proximity to the soil solution, or where those nutrients are harbored, then they can just, as long as they're in the soil solution, they can be uptaken by the plant. If it's in close proximity, that would be root interception. Mass flow is another way. So this is going to be the movement of ions in the soil solution to the root surface due to the flow of water. So mass flow is really dependent on the properties that influence water movement. So obviously this would be soil structure, aggregation, porosity, and also importantly soil water potential, whether it be matrix, osmotic, gravitational, etc. Lastly, there is diffusion. I'm sure you're all familiar with this term of diffusion, but basically it's going to be ions moving from a place of high concentration to a place of low concentration. So that would be your osmotic potential there driving the movement of water. All right, next. So also looking at nutrients, the carbon to nitrogen ratio is something you have to keep in mind. So this is just the ratio of mass of carbon to the mass of nitrogen, and it influences the rate of nutrient cycling. So basically, when you're looking at the carbon to nitrogen ratio, then you're going to have mineralization occurring between ratios of 1:1 and 25:1. Mineralization being the conversion of uh, organic nitrogen to plant available forms. So 1:1 all the way up to 25:1, then mineralization is occurring. We're converting that nitrogen to plant available forms, which is great because our plants love nitrogen. However, if you increase the ratio past 25:1, then you're going to have net immobilization starting to occur. So immobilization is just the opposite of mineralization. So it's tying down that nitrogen and plant unavailable forms to where the plants can't use it. And this is happening because the microbes in the soil, they like nitrogen. They also like carbon, but when they're getting too much carbon and not enough nitrogen, they're in survival mode. They're looking for any nitrogen they can find. So there's no nitrogen left for the plants because the microbes are eating it all. So that's really why that happens. And additionally, as the decomposable carbon increases, denitrification increases as well. So this is losing carbon to the atmosphere often as nitrous oxide. Yes, all right, next slide. All right, lastly, sources of charge. So where are these sources of charges coming from in the soil to where they can hold on to these nutrients and minerals? So soil colloids have a really large surface area. As I mentioned before, clay and organic matter are the main constituents in that. Proton dissociation, which occurs only under acidic conditions, is also a source of charge. And this occurs when an acid dissociates into a hydrogen ion and its conjugate base. Therefore, the proton loss from the surface leaves a net negative charge. Also, isomorphous substitution, which has a much higher density of charge. This occurs in most soils most of the time. And this is when one cation replaces another cation of similar size and charge. So lastly, I'd just like to touch on the 4 R's when it comes to nutrients and soil fertility. It's always important to remember to apply these nutrients at the right time, at the right place, in the right form, and in the right amount. Next slide, please. And just to wrap up, I thought I'd throw up this quote from Hugh Hammond Bennett, the father of soil health, the Soil Conservation Service, and later the NRCS. And he said, use each acre in accordance with its capability and treat each acre in accordance with its need. And here at the NRCS with our agency, I feel like this really rings true to what we're trying to accomplish. You know, it's important to not make the land work for you, but to work with the land. So yeah, and I think that'll do it. Questions, y'all?
Yeah, if you have any
Shauna?
questions.
Wait. Yeah, I have a couple of questions. First, what would you consider an ideal pH, and how does that differ for different land uses?
So an ideal pH, like you said, it differs. I mean, ideally between 6 and 8 is what we like to see. However, like you said, depending on what crops you're growing, that like for example, blueberries like acidic soil. So it depends on what you're trying to achieve. Uh, However, I showed in that little graphic, when the pH increases, the cation exchange capacity increases, which is usually a good thing, right? But you also have to you can't there's like you said, like there's depending on what you're using the land for, then a high pH, depending on why the pH is high, can be an issue. Um, so yeah, Rachel, do you have anything to add to that?
Um, yeah, I guess I would say that it's very dependent on the crop that you're growing. It's definitely true that most of them, they like something between like 6.5, like 7.5. But there can be exceptions to that, and the pH affects the availability of certain nutrients.
Mm-hmm.
So some nutrients, I think that's why the ones that are kind of acidic or like iron loving, I think, because like when it becomes more acidic or more basic, certain nutrients become more or less available. And each individual crop or plant that you're growing will have different nutrient requirements, and it cannot be all very individualized. Like
Yeah.
some do really good, and it's important to, when you're growing plants, it's important to consider that individual attention, that more or less of a certain nutrient could be better, but it just depends on the plant.
Thank you so much. And I have just one more question, if that's all right.
Yeah, of course.
So on one of the slides when you were going over ecological sites, you were discussing the site at Tejon Ranch, and you were talking about how they have like similar topography, similar parent material, but how they grow different biota. And I was wondering how that occurs.
Well, I think some of it, the Tejon Ranch, I think some of it's the elevation. I think that was a big part of it, was the changes in slope. So usually like at the lower elevations, you would see different plant communities than at like higher elevations. And so, because usually the higher up you go in elevation, there's less organic matter, and it becomes more rocky. And I think that can have a fair amount to do with it. And then the changes in elevation there can be different like precipitation levels, the temperature's different. The higher up you go in elevation, usually there's more precipitation, lower temperatures, maybe not as much organic matter as like the lower level. So does that make more sense?
I just know for like
Yeah.
example the Miocene hills, like they were similar like elevation, right? But one was grassland and one was shrubland,
Oh, okay. If you go
right?
back.
Um,
Yeah. Oh, you want to go back to that? Hold on. You can go back. Okay. Okay, you're talking about this? You're talking about
yeah,
this
yeah.
where they're like sampling from the different areas. I think it was like they're different, like they have two vegetation types. I was kind of just using this as an example. I mean, you can go, it's a publication. Like if you really want a really more detailed, because I was using it just to kind of illustrate. And I think like you could try to, I can give you a link to the publication, and then you can like read through the publication if you want to, and that would probably go into more detail than I could explain about it. But it looks like they were trying to use different sampling sites. Like it was sort of a range. They had a range to the slope. And they may have been sites that were kind of adjacent to each other. And here, because I remember, let me get, whoops. Okay, let me get the link I can put the link for that in the chat. Just give me,
While you're
I'm
doing
looking-
that, Rachel, I
yeah,
think we have another question.
okay.
Yes, we do.
From Erica. She said, "Can you clarify the difference between absorption and adsorption?" So yeah, of course. So I was trying to explain during my presentation, but basically absorption, like I said, it would be like nutrients in solution or like putting lotion on your legs. That lotion is absorbing to the deeper layer of your skin. It's not just sitting on the top, hopefully. But if I get this pen and make a mark on my hand, that's adsorbing to my skin. It's not sinking in, it's not absorbing into my skin, deeper into my skin. It's just kind of sticking or adhering to the surface. So that's the difference there. I hope that clarifies. Did that clarify? I hope.
Okay, I want to ask Rachel, are you going to respond to continue the response to this? Because it's 5 to 5, and I want to have a little bit of time just to talk to our participants.
Yeah, we can do, does anyone have like a quick question? Okay, did, did you get does the link for the publication work?
Yeah, it works. Thank you so
Okay,
much.
yeah, because I really think it's kind of a long publication. And I was just kind of trying to show like this is how people develop ecological site descriptions, but I probably can't really do that justice in like 5 minutes. I was just, if you read into it more, you can get the full explanation there.
Okay, so I want to thank Olivia and Rachel for such a well-prepared, organized, and thought through presentation. This was a great tutorial. It was a lot to absorb for all. And I have to remind students that what we do